Recording. All right. It's been forever, kind of. Hopefully you had a nice break. Missed me a little bit, maybe. Or maybe not at all. Let's see here. Oh yeah, last week we did systems of linear equations. My plan was to keep going with matrix algebra in the video, but then it was so boring to do. So I just cut it short. We'll do matrix algebra today. It's like, I love teaching online. I think it's really fun. But recording videos is like the polar opposite of that, because it's just me talking to myself and so boring. And if I'm bored of myself, that's probably not great. Anyways, I forgot to post an assignment / when I remembered, I thought, nah, they can have a break. So I posted assignment 8 just earlier this afternoon, which is on the stuff from last week. Okay. It says to use substitution or elimination. You can use whatever method you want. You can even use matrices. And so whatever method you want to use to solve, but I didn't go in and change the wording in every single one of the questions. So just kind of let loose there. And then I went ahead and posted the matrix algebra assignment, which will be from the material today. Okay, and I also posted the matrix algebra notes, and as always, brought printed copies, even though I didn't make a note of it here. We're like just running downhill towards the end of the semester, and so, which is crazy. We'll see how far we get in matrix algebra. I think we're going to finish it today, but we'll start chapter 6 on relations next day, and then that's where I'm going to cut it for the test. So we'll do test 2 review next Friday, and then we'll do functions after the test, and then we'll be done. All right. And we've got a final exam review day on the 6th, which is the very, very last day of classes. Very, very last. Okay, and then our final exam, of course, December 16th. Any questions before we start matrix algebra? Algebra, as you might know, although I used to struggle with it because I didn't really, I knew how to do, algebra, addition, subtraction, blah, 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 multiplication. But I never knew to call it algebra. And so when I heard algebra, that was really confusing to me. But it is just addition, subtraction, multiplication, division, that kind of thing. And so just kind of working with numbers. And so we're going to do matrix algebra. First thing I want to point out is that I am stealing the LaTeX code from the textbook. So LaTeX is a typesetting language. And so instead of me typing all this out, I'm just stealing it. But it's really irksome to me that they use these round brackets for the matrices. It's really weird. Steve sits behind me and he looked over my shoulder and he's like, "You're not a round bracket person, are you?" It's like, no, look in my notes, they're square. I swear, they're not. I'm not a round bracket person. I'm a square bracket person, because it's weird. But I'm also kind of lazy. And there was no quick find and replace. So a matrix looks like this, right? All the elements, we can list them, right? And so usually what we have is we need to talk about the position in an array. And so you'll be probably pretty comfortable with this kind of stuff, but we talk about the row and then the column. And so A11 is row 1, column 1, and AM3, if we have M rows, right, then we have column 3. And so here, this tells me that we have, let's see here. What can I do when you live in a shoe? We have M rows, and in this case, we have N columns. Okay. And so usually what we call it is we call it an M by N matrix, right? Rows, columns. Or it has order M by N. Yeah. And so sometimes if we need to talk about just the matrix, usually what we do is we just use a capital letter, as we've seen. And so what if we have some matrices, capital letters? Inside, if we had to talk about the entries inside the matrix, we would use a lowercase letter with the row column subscript, but we aren't going to get to that point, so you don't need to worry about that. But the order is always going to be row by column. Okay. So the number of rows by the number of columns. So if we have to find the order of A, for example, then we have 2 rows and 2 columns. So this is a 2 by 2 matrix. B has 3 rows and 1 column, making it a 3 by 1 matrix. D is a 3 by 3 matrix. That's not hard, but we need to know the order of the matrices later on. Okay. Sometimes they'll need to be the same. Sometimes they'll need to match up in a special way when we're multiplying matrices. And so being able to determine the order of the matrix is going to be important. But as you can see, it's not hard. Okay. Let's start nice and slow. A matrix A is equal to a matrix B if and only if A and B have the same order. Of course, they have to be the same size if they're going to be equal. And all corresponding entries are equal, which kind of I think is pretty obvious, right? If the 2 matrices have to be equal, then they have to be exactly equal. Okay. And so is the matrix A equal to the matrix B? So we check, okay, well, 1, they're the same size, so that's good. And then 1, 2, 3, 4, but here I have 1, 2, 3, 5, and so no, they are not equal. They're the same size, or they have the same order. Is A equal to B? Kind of silly. No, they're not the same size for one, so they're out. But also, it's just to highlight that if you only looked at the first 4 here, this would be B, right? But they're not equal. No. B doesn't have the last column of A, and also not the same order. What's nice is matrix addition behaves the way that we want it to, just kind of intuitively how we want addition to work. So if I ask you to add A and B together, what would you want to do? For me, I want to add 1 and 3. I want to add 0 and 4. I want to add 2 and -5. And I want to add -1 and 2. All right, just kind of check in and make sure that that's what you want to do too, because that's what we have to do. Okay, and so so we can read this, but that is what it's saying. Okay, and so here, right, we can add, so a plus b A and B, let's start there. A and B have to have the same order, right? M by N, they don't have to be square, but they have to be the same order. Okay? And then, of course, if they have the same shape, let's call it, then you can kind of put them on top of each other and add the entries that way. And so A plus B is going to look like this. 1 plus 3, 0 plus 4, 2 plus -5, and -1 plus 2, which we can simplify as 4, 2 minus 5, -3, and -1 plus 2 is 1. We're also asked to find b plus a. Now, logic kind of dictates that they'll be the same, right? But we'll confirm. So b plus a, the only thing that changes is the order, right? So then I have 3 plus 1, 4 plus 0, -5 plus 2, 2 plus -1. Hopefully I did that right. 4, -3, 1. Phew. They are the same. That's a nice property. Ugh, clean this up. Whee. Because we can look at these two matrices and declare that they are equal to each other, and therefore a plus b is equal to b plus a. So far, so good. I guess it is time to look at the next page, but like, don't look too hard. We'll start with scalar multiplication. So a scalar is just a number. And so if we let A be an m by n matrix and C is a scalar, so just a number, then C times A is going to be obtained by just multiplying C times every entry in A. Okay? And so if C is 3 and if A is this matrix, we're going to find C times A, which is 3 times A, 3 times 1, 3 times -2, 3 times 3, and 3 times 5, which is 3, -6, 9, and 15. So again, scalar multiplication works the way we want it to, I think, or at least I've always found it relatively intuitive. Now, well, division is just a special case of multiplication, right? If you want to divide by 3, you can just set C to be 1 over 3. Well, so if you wanted to divide, right, you could, C can be a fraction. So if you could, if you wanted to let C be 1 over 3, you're dividing by 3, right?
There'll be a power root that goes same with whatever equation.
Ah, powers. What a beautiful segue to matrix multiplication. Because matrix multiplication is special. Okay. Matrix multiplication. There's even an image to walk us through it. Okay. So let's just we'll read the formal. That was the door. Yeah. Just heard the air push. Okay, matrix multiplication is where it all unravels. If we have A is an m by n matrix, okay, m rows, n columns, and B is an n by p matrix, n rows, so same as the number of columns as the first one, with p columns, okay? Then the product of A and B, we can just write as AB, is going to be an m by p matrix, okay? So it's going to look like this. We have A and we have B. Now A, we just said, is an m by n matrix, and B is going to be an n by p matrix. If I multiply these, I get AB, of course, which is going to be an n by p, nope, m by p. Nice try, Emily. M by p matrix. So what happened here? These have to match. The insides that you're butting up against each other have to match. Okay. And then we get the results is an m by p, the outsides. So they kind of like, I think of them as just kind of merging together and eliminating the center. Okay.
Logically, it doesn't make sense. Where did the n go?
We'll see.
Logically, it's n multiplied m.
So here, this is the order of the matrix, right? It's not actually the multiplication, right? So here, this is the order. I should clarify. The order, here's the matrix, right? A times B. This is the multiplication, becomes AB.
Multiplication.
Because we're squirrely like that. Because context makes it clear. If it's lowercase, then it's the order, right? If it's capital letters, it's going to be a matrix. I guess those are things I hadn't thought about, but yeah, if it's a capital letter and you have the X, then it's multiplication. But if it's lowercase letters, it's going to be the order. Okay, then the ith row and jth column entry is going to be all the, oh boy, AI1, so whatever row you're in the first column, second column, all the way to the nth column, okay? But then overlaid with a multiplication of the column of the second matrix. Okay? I think this doesn't really help us much, but this visual will. Okay. So if we are trying to find this entry here, well, first let's start here. This is what? A 3 by 3 matrix, right? So this is a 3 by 3 and this is a 3 by 3. I expect the result to be a 3x3 matrix, right? So the result is going to look like this, which is why it's always good to know what the resulting matrix is going to look like, because then you can kind of make an empty matrix and fill it with the values that you need, and that'll kind of guide you if you've done something wonky. Okay, so if we're looking at this entry here, this is going to be a multiplication of the first row and the second column. So the first row and the second column is going to look like this. So the first row is 1 times 2 plus, so it's the sum of these things, plus the next one. Or what can I do? How can I, I think, okay, I think I've got a better way. I'm just gonna copy this and paste it there. I'm gonna copy this and I'm gonna paste it, because how I think of it is like this. In my head.
So you don't do 1 multiply 2, 1 multiply 3, 1 multiply 4, minus 1 multiply 2.
No.
You do it orderly.
Yeah, and then you sum them up.
If you're looking for middle.
So this becomes 1 times 2 plus -1 times 3 plus 0, I'll just do 0, times 4. Which
You're
is,
looking for the middle point of the 3x3.
so this,
Second column next.
this math is only to find this entry.
Oh,
It's a lot of addition and multiplication. But as long as you kind of keep your wits about you and go nice and slow. I was practicing today. It's been a while since I did matrix multiplication by hand, because obviously we use software for this stuff, but we need to know kind of how it works in case we ever need to, I don't know, program it, which someone has at some point, obviously. And so it's good to know how it works. And it's just kind of a fun exercise of being careful. And so in the office today, as I was practicing, I was like, okay, I've got this here and I've got this here. And so I'm very carefully moving through, and I am not fast at this at all. Okay. And so, but as long as you move nice and carefully, you'll get there. 2 minus 3 plus 0, -1, which matches what we have here. Right. Should we do another one of these entries? Why not? Let's do, feels weird to not have done this one. Right? Okay. First row, first column, or first row, first column. And Steve and I were joking because it's so hard to get you guys to use your fingers for matrix multiplication, but you really should be like actually have your fingers on it and kind of track it, and it will be easier. Maybe you just see it. Maybe you just are like that, but I am not. So for this entry here, let's see if we can do it. So it's going to be this row, but this column. So I get 1, negative 6. Let's see if I can do it, but I do have to use my fingers. Plus negative 1 times 3 plus 0 times 1 equals negative 6 minus 3 plus 0 minus 9. Math's not bad, but I'm pretty sure these engineering calculators do matrix multiplication, but I haven't figured out how. So, of course, I want to see your work on the test anyways, but it would be nice to be able to check your answers, right? And so, might be nice. Okay. Good. I've got another example that we'll do, so where we'll do the whole thing. So we'll keep moving. Looking at this, do you think that B times A is going to be the same as A times B? Seems weird, right? And so that's why we need to be really careful because I'll make a note here. A times B is not going to be the same as B times A. Right? And so we need to be really careful about that, because then it'll change the rows and the columns and it's completely different. So here we've already talked about it, but the product AB is only defined if you have an M by N matrix multiplied by an N by P matrix. So the inner terms have to be the same, and then they kind of dissolve and leave the two outer terms in the result. Okay. And so here, that's why we kind of start there, because it's nice to have kind of a guideline to know what A times B is going to look like. Okay. But we'll start nice and slow. First, if I have A here, A is a, let's see, 3 by 2 matrix. Okay. Then I know that I need to have 2 rows. I can have as many columns as I want, but in this case, I have a 2 by 1 matrix. And so AB will be a 3 by 1 matrix. It's good to start there. Okay. It might be nice to write out the matrices beside each other, right? Not just like this. And so I'm just going to do that, just copying it out real quick here. 1, 0, 3, 2, negative 5, 1. And then it's being multiplied, oops, by 6, 1. Okay. I've got my row, and what's nice is I only have 1 column, right? And so for the first entry, I have 1 times 6 plus 0 times 1. Then I can move on to the next row, where I have 3 times 6 plus 2 times 1. Now I can move on to the next row. Negative 5 times 6 plus 1 times 1. 6 plus 0 makes 6. 18 plus 2 makes 20. And negative 30 plus 1 is negative 29. Ta-da! Which is a 3 by 1. That's great. Yeah. I want to give you 5 minutes to try to find A times B and then find B times A. And I've already spoiled it for you, but you know they're not going to be the same. All right. So I'll pause it here. Okay. To keep things moving along here. I Martha Stewart did it. But I wrote out all the work, but notice that these two matrices are obviously not the same, right? And so the order in the multiplication matters. And so let's see here. One of the things that I like to keep an eye out for is that these values kind of stack, right? And so whatever you need to do to kind of check in with yourself and confirm that you're kind of doing the right thing, right? But pretty fun, I think, kind of problem solving, plugging away. Nice. An n by n matrix, I think intuitively you would just call it a square matrix, right? Because we know what a square is. And if A is a square matrix, then A times A is going to be denoted by A squared, and A to the power of 3 is A times A times A. But that only works if we have a square matrix, right? Because the inside and the inside values of the orders have to match, right? And so you would quickly kind of devolve if it wasn't square, right? And just for some notation, any matrices where all the entries are 0, we denote as a kind of a boldface 0 with potentially a subscript m by n, so a 0 matrix, or just a kind of a capital 0 or bold 0. We're not going to see it except in some rules where if I multiply by a 0 matrix, obviously I get a 0 matrix, right? Things like that. Okay, so I've got some examples, but I'll leave this one for you to work on your own. I'll post the solutions, obviously. But I do want to do example 9 together. We have A is 2003, and we want to find a matrix B such that A times B is a capital I. Now, capital I is called the identity matrix, which we'll see later, but it's nice to kind of introduce it early. And the identity matrix, we've seen it before, right? We've seen a matrix like this where we have ones on the diagonal and zeros around it, right? And so this is what the identity matrix looks like. And so here, if I move this out of the way temporarily and copy, I'm going to add a page here. Oh, no lines yet. matrix. Oof. Calculator down. How would you go about solving this one? So we've got A, and so we can draw that out. All right, A is a 2 by 2, and first let's tackle, okay, I want to make a 2 by 2 from the multiplication, which means that first things first, this is a 2 by 2, and I want to create a 2 by 2. I have the 2 from the outside. To be able to multiply, I have to have a 2 on the inside. And then to get a 2 on the outside, it has to be a 2 by 2. Right. So that's kind of your first step, is figuring out the size of B. What would B look like? So if we write out A is 2003. We can write out a generic B, and instead of using subscripts for kind of generic, so what we could do is we could write B11, B12, B21, B22. I don't want to do that. Let's just use A, B, C, D, right? I think that's a little bit easier to talk about, and they're just placeholders anyways. So I want to find some A, B, C, D that yields the identity matrix 1, 0, 0, 1. Now what? Okay, I can go through and I can multiply these, right? And I also know what those things have to equal, right? First row, first column, kind of laid on top of each other, has to equal 1. So we've got 2A plus 0C must be equal to 1. And if I do the next entry this way, has to be 0, right? Depending on how you like to move around. So let's see here. Then I'm going here and here has to equal 0. So I've got 2B plus 0D equals 0. Moving down. Second row, first column. I have 0A plus 3C is 0. Finally, well, we're not done, but kind of done multiplying. 0B, oops, plus 3D is equal to 1. We can simplify this. Scoot this over. Can rewrite this as 2A is equal to 1 and 2B is equal to 0. 3C is equal to 0 and 3D is equal to 1. Which means that A must be 1 over 2, B must be 0, C must be 0, and D must be 1 over 3. A is 1 over 2, B is 0, C is 0, and D is down here. One over 3. Nice. Whew. We can try it because we did find B such that A times B is the identity matrix, right? But we didn't really, we don't know if B times A is going to be the identity matrix. Okay? And so let's just try and make sure that AB is the identity matrix, but also we'll confirm that B times A is the identity matrix. Here's hoping. So we're going to check that AB, A is 2003. And B was 1/2 0, 0, 1/3. The math here with the zeros makes it a lot easier, right? Because you get 2 times 1/2 plus 0, which puts me at 1. That's good. And then I have the first row, second column. 2 times 0 plus 0 times 1/3 makes 0. That's good. That's what we wanted. Second row, first column, I get 0 times 1/2 is 0, plus 3 times 0 is 0. And last one, 0 times 0 is 0, plus 3 times 1 over 3 makes 1. So that's good.
That's an example.
Is it? We can do bigger things. We'll be able to do bigger things. That's a nice exam question, I think. But we found B using this relationship. So now the main one that we need to check is going to be that B times A also is the identity matrix. 1/2 0, 0, 1/3 2 0 0 3. Okay. First row, first column. Here we go. 1/2 times 2 plus 0 makes 1. Off to a great start. 1/2 times 0, 0, plus 0 times 3, still 0. Nice. It's exciting, isn't it? Next. Second row, first column. 0 times 2 is 0. 1/3 times 0 is 0. Finally, 0 times 0 is 0. 1/3 times 3 is 1. Whee! We're so happy. Okay. So what we're going to find is that B is called the inverse of A. So when AB is equal to the identity matrix, which is also equal to BA, we say B is the inverse of A. or vice versa. Even though it looks like it has a nice kind of reciprocal property, that's not the case. Okay, so don't be fooled by this itty bitty example, because I'll show you how to find the inverse on the next page. So this example 9 is the one we did together. And then what I want you to do is I'll leave example 10 for you to work through on your own, which has kind of been split across the pages here. Sorry about that. But you have them printed out. So it's just translating these systems of equations into matrices. So you don't have to solve them or anything. So matrices are used a lot. Linear algebra, programming, optimization, but also most upper level statistics is based on matrix math. So it's out there, but we never have to see it anymore. So it's this kind of silent killer, if you will. A diagonal matrix. We've seen a diagonal matrix before, right? A diagonal matrix is whenever we have 0 terms, whenever the row number and the column number are not the same. And so some diagonal matrices include things like this, but I also want you to see something like this, where, right, even though we have a 0 there, it's allowed to be 0. The only condition is that, okay, if the rows and the column numbers are different, then it has to be 0, but the diagonal is also allowed to be 0, which is kind of confusing, I think. So I wanted to point that out. But then, of course, the most common diagonal matrix is the identity matrix. So the identity matrix, we've already seen it, we've already used it, has the property that blah, 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 that the identity matrix kind of operates like a 1 does in regular math, right? A times 1 is the same as 1 times A, which is just A, okay? And so A, yeah. So the identity matrix behaves in matrix algebra like the real number 1. For example, 1 times A is the same as A times 1, which is just A. So no matter which way you slice it and dice it, you can multiply them and you'll just get A back. Usually what we do is we use that fact, but we use kind of a convenient value of 1, which we've done in the past, right? We've kind of said, okay, well, things like 3/3 is 1, and maybe it simplifies our work a little bit, right? And so we do that with matrices as well. Okay. And so the identity matrix is an n by n, so it has to be square. Okay? And so square. And it's a diagonal matrix where all the diagonal components are 1s. And so sometimes or often we just use a capital I to indicate that it's a matrix, capital, but also I for the identity. So you don't want to use I for a different matrix because it's special. But I feel like you guys know all about those kind of reserved variable names, things you can't use. Okay. So like I said, what we just found earlier was the inverse. So if A is a square n by n matrix, then there could exist a matrix B such that AB is the same as B times A, so that's pretty rare, and it is the identity matrix. Okay. And so then we call B the inverse or a multiplicative inverse of A. We just call it the inverse of A, and we denote it by A to the -1. So we can prove that inverses are unique. If they exist, they are unique. Okay? And I'll show you when they don't exist. It can happen. But the inverse of an n by n matrix A, when it exists, is unique. So the proof looks like this. And it's just itty bitty. And so that's why I wanted to include it. It does jump ahead. See page, whatever the last page has all the laws of matrix algebra. So I even gasped when I was working through these kind of more carefully today. Said, hey, they haven't introduced the matrix laws yet. And they're using them, rude. Anyways, I think we're okay with it. I'll walk you through it. So if we have A, then let's say for a moment that, because we're trying to show that the inverse is unique. So usually how we do it is by contradiction. And so we say, okay, let's assume that it does have two unique inverses, B and C. Okay? Then what we can do is we can say, okay, well, let's start with B. And then I know that if I multiply by the identity, then it just is B. So that's still true, right? Then if we assume that C is also an inverse of A, then we know that this is a convenient version of the identity matrix, right? A times the inverse of A is the identity, right? And so we replace the identity matrix by A times C. So now I have B times A times C, right? A times C first and then times B. But then as a rule, and I'll tell you this, as long as the order of the multiplication doesn't change, right? Then you're allowed to regroup. Okay? Just like A times B times C, if we're thinking kind of normal algebra, is the same as A times B times C, right? So it behaves the same way, right? As long as the order is preserved, then I'm allowed to regroup these things. But what that means is that, okay, if I regroup these, then if B is also an inverse of A, it must be the identity matrix, right? If I multiply those two by the rules, I'm back to the identity matrix. But then the identity matrix times C is just C, because that's how the identity matrix works. Therefore, therefore, B must be equal to C. And the inverse is unique. So that's kind of fun. I think that's a nice kind of baby proof. Right? Not something that I would get you to do, because knowing where to start here takes a lot of practice. And once you've done enough proofs, you would know, okay, well, I think I'm going to throw in a convenient value of 1 and see what happens, right? But that's not an obvious place to start, right? But with practice, you start to kind of see these kind of go-to moves. But here's a proof, a little itty bitty proof. We did it. So what is the inverse of A? And so what we're going to have is we'll have a formula that is going to let us compute at least a 2 by 2 matrix, and then the formula becomes too complicated. And so I'm going to show you just an algorithm that's always going to work. And I actually prefer the algorithm, but I felt bad not showing you this kind of quicker way for a 2 by 2 matrix. Okay, so it only works for a 2 by 2 matrix. But to do that, we first need to talk about what the determinant is, the determinant of a 2 by 2 matrix. So if we have some generic A, which has entries A, B, C, D, just like we did earlier, right? I didn't pull it out of nowhere. Then the determinant of A is the number, and we use det A, or if you prefer, I'm going to try not to, but it's kind of like the absolute value of A, but when A is a matrix, it's implied that it's the determinant. And so I'm going to just write det A. And don't worry, we had a big discussion today about when you would use which notation. I'm fine with either. I'll understand if you prefer the vertical bars. I do, but to match these notes, I'll just write det A. Now, the determinant of A is going to be A times D minus B times C. All right, so it's kind of like this diagonal crisscross applesauce. Copy, paste. So it becomes this A times D minus B times C. Which is just going to be a number. It's not going to be the inverse, but it is something that we need in order to find the inverse using the shortcut. So if we have A and B, we're going to find the determinant of A and the determinant of B. So let's see what we got here. The determinant of A is going to be 1 times 5 minus 2 times negative 3, right? And you just kind of, I guess, memorize this crisscross applesauce. Right. So we get 1 times 5 minus 2 times negative 3, which is 5 plus 6, which is 11. I guess I should write that out. Nice. Later, we'll use that number. But we need some practice finding the determinant first. How about the determinant of B? 1 times 4 minus 2 times 2. Is 4 minus 4, which is 0. Interesting. Now, what that means is that there is no inverse. So if the determinant is 0, there is no inverse. And we saw that, right? Here, right? The inverse, when it exists, is unique. Right? And so there are instances where the determinant is 0, and so then that means that just tells you that there is no inverse. Okay. Any questions so far? The inverse. Now, I will highlight that this is just for a 2x2 matrix. If we have this generic A, which is A, B, C, D, and as long as the determinant of A is not 0, then the inverse of A is going to be 1 over the determinant of A. So that's where we would use the determinant that we just calculated. And times, so that's a scalar multiple of D, negative B, negative C, A. More crisscross applesauce. Here, it looks like this. These two switch. Right? DNA switched, and B and C stay in place but are negatives. To get to here.
It's negative. It means it.
Yeah, it's times -1.
So it's minus C and B. It'll just delete minus C.
Yeah, so if C was -3, then negative C would be 3. Yeah. Got an example just like that. Here we have A. We're going to find the inverse. We only have this one method so far. All right. And so let's get to it. First thing, right, is to find the determinant of A. I'm pretty sure it's the same as the A it is. So we already found the determinant, but we can do it again for practice. I don't see any harm in that. The determinant of A is 1 times 5 minus 2 times -3. 5 plus 6 is 11. Still. So this is kind of step 1.
Or you could also do crisscross 1 and 5 and 2 and -3 and find that way as well. Do that way.
No, we need the determinant. Do you mean to get to this?
Yeah.
So we also have to do that. But here we're finding this part. That little guy. So then in step 2, let's see here. A inverse is 1 over the determinant of A, which is 11. So it's just a number. And that's why if it was 0, if the determinant was 0, I can't divide by 0. It doesn't exist. And so that's why there would be no inverse, right? But that's just a scalar multiple as a fraction, just like you wanted. You wanted this. And I have to switcheroo these. So 1 and 5 switch spots, and B and C are negated. So here, 5 and 1, I like to start with those switched first, and then -2, -3. Do you mean these ones?
No.
No, you don't switch them because it used to be A, B, C, D, D, B, C, A. So the only ones that switch here are the diagonals, but B and C are negated. Just like that.
I saw something that I don't want to see. Something that is logarithm matrix.
No, an algorithm. Yeah, don't worry, no logs. Although I guess we probably could, but no, we can't. So now this is just a scalar multiple, right? And so I can multiply this in and I get 5/11, -2/11, 3/11, and 1/11 is the inverse of A, and that's step 2. Making sure that you've swapped these and you've negated the other terms. So even though we had that cute example where it was just that actual inverses of the entries, that's not the case. Right? It was a very convenient example, but the inverse can be kind of nasty. I want to show you, I can't call it my way because it's a very common way algorithm for finding the inverse. But I'm curious to know which one you like better. Steve likes this way better for a 2x2, but then you kind of tap out. There is a way to do it for a 3x3 matrix, but it's way too complicated. It's kind of the same, but how do you crisscross applesauce in a 3x3? No, I'm going to show you a way that always works. But first, if A is a 2x2 matrix and the determinant is 0, then the inverse does not exist. We already saw that, right? And a formula for the inverse of n by n matrices can be derived that also involve the determinant of A. I'm sure a lot of people at some point got a lot of PhDs at some point kind of figuring out what the determinant of a 3x3 or a 4x4 or 5x5 is. But we've got kind of better ways. And so in general, if the determinant is 0, then there is no inverse. And so, and just as a side note, the inversion comes first in the hierarchy of matrix operations. So if you see A, B inverse, then you would do the inverse of B first and then multiply those two together, right? And so I'll highlight that because that's kind of just snuck in there, but that's important to remember that you have to do the inverse first and then you can multiply them. Okay. Here's what I'll call my way. It's not my way. It's a very common way of, so the algorithm for finding the inverse of A of any n by n matrix. So as long as it's square, we can find the inverse if it exists. What we're going to do is we're going to row reduce, going back to working with our matrices, those row operations. We're going to row reduce the augmented matrix where I take A, and what I like to do is I like to draw a bar. So I have my matrix A, and then I augment the same size identity matrix. And then what we're going to do is we're going to rework it until, so we do row operations until I have the identity matrix on the left-hand side, and then the result is the inverse on the right-hand side. Neat. And that's going to work for any n by n matrix. First,
Inverse doesn't exist.
this one. Oh, it does.
That's 0.
Oh, but we're appending the identity matrix. So what this is going to look like, so we're going to find the inverse, but I am actually kind of tempted to start with this one because we already know what the inverse is, and it's itty bitty, and why not? So I'm just going to add a page here, and I'm going to snag this here just to show you what I mean. That might be nice. Use the algorithm to find the inverse, because it'll work for a 2x2, but it'll also work for any square matrix if there is an inverse. What you'll find is you won't be able to row reduce to the identity matrix on the left-hand side if there is no inverse. And so that's how it kind of rears its ugly head. Now, maybe I should be more careful here. So if I have A augmented with the identity matrix, like I said, usually I like to visually separate them with a line. You don't have to, but I find that it's really helpful. So what this is going to look like is you have 1, 2, -3, 5, whoop, and then the same size identity matrix, 1, 0, 0, 1. So what we're going to do is we're going to row reduce this left-hand side, but that's also going to manipulate this side, right? As we turn this into the identity matrix, like that's right, that's our goal. Then this side is going to be kind of massaged to be the inverse of A. So convenient that we have a value of 1 here. So I'm gonna first kind of dust off my row operations, right? And I'm gonna say, okay, first thing I'm gonna do is I'm gonna take row 2 and I'm gonna add 3R1. Because my number one goal to start is to create a 1 here, but I already have a 1, so that step's done. And now I'm going to eliminate this and turn this into a 0. And then the next thing I'm going to do is I'm going to turn this into a 1, and then I'm going to use that 1 against this 2 to make that 0. Right? That's all from last week, but it's been a long time, so. All right. First row stays the same, so usually I just like to write those out. Okay. -3 plus 3 times 1 is 0, just as we planned. 5 plus 3 times 2 is 11. Making sure you do the right-hand side. I had to do the left and right. The right-hand side as well, right? 0 plus 3 times 1 is 3. 1 plus 3 times 0 is 1. Next thing I'm going to do is I'm going to turn that 11 into a 1. And I'm going to do it on this line here, 1 over 11 times row 2. I'm going to squeeze it in here. 1, 2, 1, 0. Oops, 0. 0 divided by 11 is 0. 11 divided by 11 is exactly what we wanted, 1. 3 divided by 11. Usually we'd be upset by that, but we also kind of saw it coming, right? Because if we glance back at the inverse, that is the value that we wanted. So that's good. And then 1 divided by 11 is also good. Now we want to pivot around this lower one to eliminate the 2, right? And so to do that, we're going to take row 1 minus 2 times row 2. 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0, just like we planned. That's great. This is where it gets a little bit messy. 1 minus 2 times 3 over 11 makes 2 times 3 is negative 6 over 11. Right? Oh, but then 1 minus 6 over 11. Can I cheat and use my calculator? 1 minus 6 over 11. I get 5 over 11. Oops. Because it's row 1 minus 2 times row 2. 1 minus 2 times 3 over 11. So 1 minus 6 over 11 is 11 minus 6, which is 5 over 11. There. Then 0 minus 2 over 11. That's nice. Negative 2 over 11. And just like that, we're done. Same inverse as we found earlier. I'll say in example 12. Now I'm curious. Do you like the determinant way or the augmentation way? The determinant. You're going to memorize all those crisscross applesauces. I definitely prefer this way because I don't want to memorize the determinant and I don't want to memorize the switcheroos, but it's completely up to you. If I give you a 2 by 2 matrix, you can find the inverse however you want.
Are you gonna give us 3 by 3?
The determinant way? No.
Then isn't it more easier to cross rather than
Well, because it only works for a 2 by 2, you're fine. It's fine to use it, but it only works for a 2 by 2. Whereas the augmentation, so this way, works for any square matrix.
we're only doing 2 by 2?
No.
There's no 3 by 3.
We're not doing the determinant way.
Oh.
It exists. You can Google it, but I didn't even look at it. No, thank you. I have this vague memory of learning it, but a nightmare. But we've got this easy way. So now we're going to find the inverse of this 3 by 3 matrix if it exists, which it does. So you're gonna augment the matrix with a 3 by 3 identity matrix. And what I'll do is I'll give you time to work on it, but also I'll write it out in the video kind of, but I'm not going to read out the numbers because it's pretty distracting, but I want you to try it. So what's this thing going to look like? 0, 1, 2, 1, 0, 3, 4, -3, -3, 8. I just said I wasn't going to read them out. That's so I could copy them down. And then the identity matrix, the 3 by 3 identity matrix, which is going to morph into the inverse. Same tricks apply, right? I would say, okay, I'm gonna scope out kind of what would make my life easier. I'm allowed to rearrange rows. As long as I rearrange the entire rows, then that's allowed, right? And so I see a leading one here, and then this one is a second one. So how about I just kind of switcheroo these and start there instead. Otherwise, you'd have to turn this into a 1. What a mess. Is there someone at the door? No? Oh, they can come in. Learn how to augment the matrix. You can come in. We're augmenting the matrix.
What's
So
wait,
low,
it's so
it's
heavy.
so low.
You guys are not on that. No, we're not.
Well, buckle up.
We're currently doing like trick.
Yeah. Doing slopes and stuff.
Are you guys in Susan's section? Paul's?
Yeah.
Who knows what that guy's doing?
Yeah, he says he's going out of book.
He always does. I'm going to switcheroo R1 and R2. There you go.
Do you?
I know matrices. I know how to do the inverse. It's like a big thing. They're like 2, 3 methods to do.
As long as you float the entire row, even though I've got them separated, but that's a make-believe separation. And then the last row, -3, 8, stays the same. Now, remember our goal is to eliminate, so turn all the ones or all the values below the ones into zeros. And so the easiest way to do that is going to be to take row 3 minus 4 times row 1. So here we go. Row 3 minus 4 times row 1. All right. Row 1 stays the same, row 2 stays the same, so I'm going to write them out, and then we're manipulating row 3. So 1, 0, 3, 0, 1, 0, 0, 1, 2. I just said I wasn't going to read out the numbers. Oh, here we are. Okay, here we go. 4 minus 4 times 1 is 0. That is as planned. -3 minus 4 times 0, that's a relief, is -3. 8 minus 4 times 3 is -4. Okay. 0 minus 4 times 0, 0. 0 minus 4 times 1 It's -4. 1 minus 4 times 0 is 1.
But as you get to the -4 again,
This one or this one?
right.
This one? It is from 0 minus 4 times 1. Good. From our clever switcheroo in the beginning, I already have a 0 above the 1 on the diagonal here, but I'm going to turn this 3 into a 0 by taking row 3 plus 3 times row 2. Okay.
So I have a question. Why did we pick the row 3? Why not row 2 or row 4?
Like as the next thing to do. So what we're going to do, so the general mechanism is to turn this entry into a 1, then turn all the values below it into 0. Then when you're done that, then you turn the next one on the diagonal into a 1 and use it against the other terms to turn them into zeros. And then finally you start picking away at this one, turn it into a 1 and chip away at these and turn them into zeros. Right, so you're kind of cascading down the diagonal. So then to turn this into a 0, we're going to have row 3 plus 3 times row 2. Okay. Rows 1 and 2 stay the same, so I'm just going to jot them down. 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0. Row 3, just confirm 0 plus 3 times 0 is 0. -3 plus 3 times 1 is 0, so that's good. Here's where it might get a little bit messy. -4 plus 3 times 2. -4 plus 6 is 2. 0 plus 3 times 1 is 3. -4 plus 3 times 0 is still -4. And 1 plus 3 times 0 is still 1. You could do something sneaky and you could say, okay, well, what if I didn't turn this into a 1 and I just used it to turn this into a 0? You're allowed to do that, but I'm going to stick with the script and just turn this into a 1 and then use that 1 to turn on the other two.
So next one will be row 2 minus 2. 1.
We need to turn this into 1 first. So 1/2 times row 3 before we can do it. 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0. And then 1/2 times row 3 is 0, 0, 1. 3 over 2, -4 over 2, which I'm going to write as -2, and then 1 over 2. Ooh, fractions, gross. Which is one of the reasons that you might have, if you wanted to, and if you see it, right, then you could have turned this into a 0 using this 2, right? Done row 2 minus row 3 and then turned it into a 1, and then you only need to work with fractions to eliminate the 3. Doesn't matter, but you're allowed to do that as long as you end up with the identity matrix And now, because I'm manipulating row 2 and row 1, just kind of individually, I'm going to do them in the same maneuver. Row 1 minus 3 times row 3, right? And then for row 2 minus 2 times row 3. Just skipped a crucial step. Okay, let's start with row 1. 1 minus 3 times 0 is 1. 0 minus 3 times 0 is 0. 3 minus 3 times 1 is 0, which is what we were going for, of course. Oops. Okay. 0 minus 3 times 3 over 2 is negative 9 over 2. One minus 3 times negative 2 is 1 plus 6, which is 7. 0 minus 3 times 1/2 is 0 minus 3 over 2, which is negative 3 over 2.
Middle part, the 7.
Yep.
Sure.
1 minus 3 times negative 2. 3 times negative 2 is negative 6. 1 minus negative 6 is 1 plus 6, which is 7. Sneaky, right? Okay. Whew. That's this part done. Now we're going to manipulate row 2 by subtracting 2 times row 3. Don't do what I did when I was running through my notes and try to do minus 3. It's not going to work. And so just, okay, row 2, new calculation. It's going to be 0 minus 2 times 0. That's still 0. 1 minus 2 times 0 is still 1. That's why we work on the diagonal, is because we're not manipulating things that we've already tweaked. Then 2 minus 2 times 1 makes it 0, just like we wanted. 0, 1, 0. 1 minus 2 times 3 over 2 is 1 minus 3, which is negative 2. 0 minus 2 times negative 2, yep, is 4. 0 minus 2 times 1/2. Oh, it's, yeah, negative 1. And then row 3 is good to go. 3 over 2, negative 2, and 1/2.
So those are A, B, C.
Mm.
And then we're changing-
No, so here, this is now the inverse of A.
And this is coding that.
Yeah. We just spent like almost an hour doing it. Of course it is.
That's gonna be like 8 marks. That'll take like, as I said, an hour, so.
Well, it's quick. It's breezy when you're just doing it on your own.
It has another method. Do they do it by
Remind me this class.
A versus joint A by determinant A?
That only works for a 2x2.
No.
Well, there is a determinant for a 3x3, but I'm not teaching it because this way is faster. You can check that A times A inverse should be the identity matrix. And if you're still unsure, or maybe just want to do some matrix multiplication, you can also check that the A inverse times A is also the identity matrix. Nice. Now you know my way of, it's not my way, my favorite way of finding the inverse. There's some practice problems here, some laws of matrix algebra. We've already seen, which one was it? We already saw the associative law of multiplication, right? And so the main one is that addition works, right? It's commutative. A plus B is the same as B plus A, but nowhere on here does it say that A times B is the same as B times A, because we saw it multiple times that that is not true. And so as an exercise, I get you to write out what the orders would be or would have to be, or kind of are implied. And so they show you how to do law 10, right? But I want you to rewrite those other laws specifying the orders of the matrices, and then do a little practice, and that's it. Just like that. If you have any questions, let me know. Otherwise, I release you just in the nick of time, I think. Who knows?
This was the most interesting class.